Hi, welcome to the demo about Lakeflow Spark Declarative Pipelines. So, in this demo we are going to see different incremental reference strategies, namely the append strategy alongside the partition override. We are also going to see how this append strategy and the window strategy can be broken, and we will also cover the aggregate and row and window refresh strategies. And let me just set up the environment for the demo, deploy the bundle, and set up some SQL queries. Okay, these are my queries. I will create a regular table with a few rows inside that I will first use in the aggregation strategies demos. Okay, the query has completed. And let's see the generic aggregate demo. And so I'm starting the pipeline now. And while the query is running, we are going to see the transformation applied in this pipeline, which is a simple grouping by number and distinct count of words, like words inside each group. So the query is, of course, executed now with the complete recompute because is the first execution, so that's something normal. And now I'm going to add the new records to the table and restart the pipeline to see the generic aggregation strategy in action. So here I just added a few new distinct words to the group with number 1. And as you can see, we have the incremental strategy with the generic aggregate optimization, meaning that there is only one group that will be impacted here. Okay, let's see now something else, which is the group aggregate. Group aggregate query is a little bit different because here I'm grouping by number over yet again, but I'm creating various aggregations for each group, like the count and min and max. So I will modify some data in the table later, and now I will start the query just to get the fully recomputed table. Okay, the query is setting the tables up, and as expected, the first executed strategy, incremental strategy, will be the complete recompute. Okay, and now it's time to change some data, add a new longest word to the group, and run the pipeline again to show you another incremental strategy, refresh strategy in action. So this incremental strategy will be this time the group aggregate, meaning that we are going to refresh the aggregates from this particular group. Okay, let me close the windows and see another pipeline, which will be the window pipeline, the pipeline with some window aggregation. And then what about the code? The code here uses a window partitioned by number and ordered by word, so that we can get a sequence with previous and next words in the window, so in the list in our case. So the pipeline is running, and as previously, it will start by the full recompute incremental strategy. Well, it's not a real incremental strategy, but it's under the same column. Let me now modify the data, add some other words to the window. That will slightly modify the list and the part belonging to the number 1. And now I will refresh the pipeline and see whether this is the window function strategy that was picked by Lakeflow Spark Declarative Pipelines runner, which is under the hood the enzyme engine. And as you can see here, the window function is much cheaper, almost twice cheaper than the full complete recompute strategy. Okay, let's see now the fourth strategy, which is the append-only. And here the transformation, the logic is very simple. We are taking the data from the partition table and we are writing it to another table partitioned by number. So we are just copying the data, in fact. And this very simple demo will show you two optimization strategies, the append strategy and the partition override. So again, let me run the pipeline first on top of a partitioned table by number. As you can see, the strategy is full recompute. And now I will do the first modification, which is a new row for each partition. So partition 1, 2, 3, and 4. And now, when I run the pipeline, you will see that Lakeflow will pick an append-only, an append incremental strategy, append-only strategy, as that's the exact name. And now I will replace a particular row inside the partition number 1. And you will see that this time the strategy will be different than the append-only, because we are modifying a single partition, right? So there is no reason to do an append job or to do anything else. So let's the pipeline running for a few seconds, and yeah, we have the button, and you can see that the incremental strategy was the partition override, and it was slightly cheaper than the row-based update. And regarding the row-based update, that's something we are going to see next. Okay, and about the code for this part, it will be very similar to the previous demo because we are also copying the data, but unlike previously we were using a partition table, now we are using a simple table, so a table without partition. So let's just compare the code snippets for the sake of visibility, like opening now the append-only demo, remember, and you can see that we are creating materialized view for both cases, but for the append-only we are using the number partition. And this is very important because you will see it, that despite a similar modification, this row-based demo will use the row-based strategy. But first things first, and here is the first execution that obviously will end up with the full recompute strategy. Yeah, that's something that was expected. And now I will going to do a change. So the change is the same change as previously. I'm changing a row in the whole table. And because my materialized view here is not partitioned, Lakeflow will not be able to use the partition override strategy. Instead, it will rely on the row-based strategy. Okay, we have the pipeline running, and the incremental button should be showed up in some time. Yes, we now have the incremental information, and as you can see, it is the row-based strategy. And if you compare it with the full recompute, you can see that it's like much more cheaper to do. Okay, and we will end up with two code snippets that show how to break an incremental strategy. First, we are going to break our append demo with a random value. Random value is very problematic for the incremental reference because it's not deterministic. And you will see this, by the way, in a few minutes after we refresh this pipeline for the second time, that the enzyme engine will not be able to generate a consistent fingerprint from the query and apply a deterministic refresh, incremental refresh. So of course the first execution is because of the empty table is marked as the for recompute, but now when I add some data to the table and try to apply logically the same strategy like before, I will be a little bit disappointed because, as you can see, the incremental is not used. We are using the complete recompute strategy, and this is because this incrementalization issue with the query fingerprinting changing every time, that preventing incrementalization. And here you can also see somewhere the information about the yes, the issue type. Plan is not deterministic, so obviously we cannot run the predictable incrementalization. Another issue you can encounter is when you use a global window, so a window without the partition by clause. So as you can see, we have just a global window ordered by word. So we would like to build maybe a list of tokens like in our new LLM based word. But unfortunately, this approach will not work with the incremental refresh strategies, because you will see later there is also one specific issue pinpointed by the enzyme engine. So now the pipeline is running. I will add some data to the numbers table, and later on I will restart the query with this new data on top of the input table. And as you can see, the incremental strategy is complete recompute, simply because the window function, there is somewhere indicated here, yes, the window function is missing this partition by clause that can clearly identify the groups to update. And yeah, that was all for this short demo about incremental strategies. If you want to discover more on that, I invite you to the article which is linked in the description of this video. It was Bartosz Konieczny from waitingforcode.com. Thanks for watching.